Okay, now let's talk about the action potential. The true action potential, the one that we're going to be talking about, it occurs in the axon, but only in the axon of unmyelinated neuron. The moment you start to myelinate the axon, the moment you put on myelinated sheets made by either Schwann cells or oligodendrocytes, then the mechanisms are still present, but the true action potential, it is not. So now you're going to be talking about true action potential. And so let's zoom in here in the vicinity of axon hillock. Okay, so this is the part of the axon just adjacent to the axon hillock. So I drew three structures here. This green one is the sodium potassium pump, the one that you already know. Okay, and then in red, voltage gated sodium channel. And the one in the blue is voltage gated potassium channel. And just a reminder, here on the membrane, you have that 70 millivolt potential. Okay, and so now everything is ready. All the structures that we need are set up. And now let's talk about how the action potential work. So you know that when the synapse or an axon fires, right? When you have, let's say, some axosomatic synapse, it triggers the influx of sodium ions inside the cell. Okay, so let's draw it here, right? So let's say you have a synapse here of some neuron here in the distance. Okay, and when this synapse fires, it triggers the influx of ions inside the cell. Okay, there are actually many things that can happen after synapse fires, but the influx of ions is the most common. And now what happens? The concentration of that given ion will increase, and they will start to diffuse away from the area of the synapse until they will reach eventually axon hillock. Okay, here at the axon hillock, normally there's minus 70 millivolts on the membrane, and let's say that the action potential will fire at the moment when the voltage will increase to, let's say, minus 50 millivolts, right? So then we would say that the threshold for action potential would be minus 10 millivolts. Yeah? And what will happen if all these positive ions will start reaching the external hillock? That will increase the voltage on the membrane from minus 70 towards and maybe beyond the minus 50, right? And if it passes the minus 50 barrier, then the action potential will fire and travel down the axon all the way to the terminal arborization. And now, how does this work? So let's come back to our drawing. You have all the ions from saltatory conduction arriving here to the area of the hillock. Right? Here you have the voltage gated sodium channels, would be these, right? And these sodium channels, they are closed at the resting state. They are closed when the voltage on the membrane is minus 50, but they open when the voltage is minus 50. Right? And so what will happen is that if there's some small increase of voltage or relatively small increase of voltage here inside the axon, it will open these sodium channels and will trigger influx of even more positive sodium ions. All these will enter. Now you will have a huge increase in sodium ion concentration, and also you will have a huge increase in the voltage. Okay, and so here in this area, instead of minus 70, you actually might get to 0 and maybe even positive numbers. Let's say up to plus 20 millivolts here at the area of the voltage gated sodium channel. And as you go like further away from this voltage gated sodium channel, yes, the voltage will decrease because the concentration of positive ion decreases. However, here just next door you have other voltage gated sodium channel. And so if here the voltage is plus 20, here maybe it will reach minus 20, minus 30, minus 40, which is still above the threshold of minus 50. And therefore this sodium channel will also open and all these sodium ions will enter as well. And I think you get what's happening, right? Then all these sodium ions will diffuse towards this channel, which will also fire. And it will let the sodium channels in. And this keeps happening all along the length of the axon until you reach the end of the axon in the terminal buttons. Actually, what happened initially, you had some negative charge on the membrane. Here I'm going to draw the voltage, right? So it was positive outside and negative on the inside of the cell. But then what happened is that these actually flipped. So instead, you got positive voltage on the inside and negative on the outside, because all of the sodium ions are entering the cell. Okay, and this is good for relaying the information, but there's a problem, right? This state is not the resting state. So yes, the information is going the right way and to reach the end of the axon. But if you wanted the axon to fire again, the cell will not react, right? Because now the sodium channels are like still open, and it will reach the end of the axon one way or another. So if you want to send two pulses, two signals, you need to reset after each. And so how that happens? How do you return the membrane potential back to its original state? Is this. On the membrane, you have those voltage gated potassium channels. That's here. Right? What I did not draw is inside you have an overwhelming amount of potassium ions all over here. Right? And at the moment when the action potential passes through this area, these potassium channels will open. Right? And how do the potassium channels know that they should open? Because maybe they open at, let's say, 0 millivolts. Right? The numbers don't have to be necessarily correct. They also definitely differ between types of the cells, but you get the idea, right? At the peak or near the peak of the action potential, when the cell is already filled, so the axon is already filled with the sodium ions, the voltage gated potassium channels will open and they will let the potassium move out. Right? So all the potassium will start to leave the cell. And these are positive ions leaving the cell. And so this will lead to decrease of the electric potential inside the cell. Right? So after this, the charge on the membrane will go back to normal. So you have negative on the inside and positive on the outside again. See? And what happened? First, we had that action potential traveling through that was maintained by the voltage gated sodium channels, and then we needed to restore the original electric potential of the membrane, and that's why we have the voltage gated potassium channels. Yeah, voltage gated sodium channels open at the beginning, when the action potential starts to lift off, and after some time, with some delay, the voltage gated channels open as well, and they restore the membrane potential. And now, this on its own would lead to a state where you deplete all the sodium from the outside and you push it inside the cell, and all of the potassium from the inside will be pushed outside. And that's why you need that sodium potassium pump, which will be taking those sodium ions from the outside and putting it in. Yeah, the sodium potassium pump is actually spread all throughout the membrane, but too cluttered if I draw it. Just know that it's there, present, doing its thing. Okay, and so I told you that the true action potential occurs only in an axon that's non-myelinated. So what happens in a myelinated axon? So here you have your myelin sheets, you already know, and here in between them you have these clefts where they are not covered by the myelin. These clefts are called nodes of Ranvier, And these are the parts of the axon where the mechanism is similar to the action potential, in that you have those sodium and potassium voltage gated channels, right? And they work exactly the same here at the nodes of Ranvier. However, in between the nodes of Ranvier, you have this saltatory conduction occurring. And the reason why we have this is that this way it's way faster. The action potential is good because the action potential does not dissipate over distance. So the action potential will definitely get the information across to the end of the axon. But saltatory conduction is really fast, right? And at some distances, maybe 1 micrometer distance, the saltatory conduction is still strong enough not to dissipate. And so that's why you have those myelin sheets, right? Actually, what's happening is that here at the beginning of the axon, the action potential will fire. This will, let's say, increase the concentration of the positive ions here, and they will start to diffuse through here, right? And here towards the end of the myelin sheet, the concentration starts to get a little bit low, and that's why here you have again influx by the voltage gated sodium channels, and then those sodium ions slowly dissipate on the inside of the axon that's wrapped in the myelin sheet, right? And here again, increase the concentration, and etc., etc., etc. Right? Which leads me to the function of the myelin sheet, right? Why do you even have them? There are two functions that you need to know. One is immediately obvious, is that myelin sheets increase the speed of the signal conduction through the axon. Okay? Myelinated axons carry the signal way faster than non-myelinated. First function, speed. Second function, insulation. Right? You know that when you have some wire that conveys some electricity or electric signal, it's always wrapped in rubber, right? So if you put it next to another wire, so the say electric signal doesn't skip from one wire to another. So that's why you have some wrapping around the zone.